Today we are going to discuss about magnons in ferromagnetism. The Weis molecular field theory failed to explain many things. For example, the magnetization value, especially at low temperature, so that a new model of spin waves is needed. That is, we call the magnons, which is actually a quantized form of spin waves. So it's actually a quantum mechanical approach in ferromagnetism. And now we will consider a one-dimensional ferromagnetic chain. As you see here, suppose there are n number of spins. So this is actually a lowest energy configuration because the entropy is the least. So what will be the exchange energy? So that is given by this expression, that is U is equal to minus 2j summation sp dot sp plus 1, where j is an exchange integral. H cross sp is called the angular momentum of the spin. Now if you are treating it as a classical vector, this sp dot sp plus 1 can be equal to s square, so that the exchange energy u0 is equal to minus 2j into n minus 1 into s square. Since this n minus 1, because if there are n spins, the number of pairs will be n minus 1. Now we consider an excited state where with one spin is reversed. Out of these spins, we are reversing one of the spins. So when we are flipping these spins, there are two pairs will be less in the upspin, and there will be two pairs will be created with opposite spin, so that the new exchange energy can be written as u1 is equal to minus 2j n minus 3, because there are n minus 3 pairs in the upward direction, into s square plus 2 into 2j s square. So this can be written as in this form. So we can take it as u0 plus 8j s square. So that is the new exchange energy. Hence we can see that on spin reversal, the exchange energy is increases by a factor 8j s square. We can form an excitation of much lower energy if we let all these spins share the reversal, as you see here. So we can have the same effect, but energy is lower. The spins, each spin will share the tilt. This is actually a quantum mechanical approach, and the elementary excitation of these spin waves are called magnons. So if you go around one complete cycle, the magnetization should be 0 according to the classical theory, the molecular field theory, so that the corresponding energy is E is equal to m dot minus m dot b. So if magnetization is 0, means E is equal to 0. So that is a higher energy state. But if we consider the nearest neighbor spins, and each pair will be tilted by a very small angle, as you see here, so that the energy for neighboring spin pairs will be, we can write it as minus 2j dot x 2j x1 dot x2. And if you consider the angle theta is very smaller with between neighboring spins, so that we can neglect, we can consider cos theta is equal to 1, so that this will be minus 2j square. So like that, if you consider each neighboring spins, the theta value is much smaller, so that the effective exchange energy will be a value, some value is there, so that is higher than what is predicted by the molecular field theory. So here we consider the first excitations, that is, we take one spins and we consider the reversal of a single spin. So that is the first excitation stage, and such spin excitations also called spin waves. So now we need to derive the dispersion relation, that is how the energy depends on k value. For that, this involved the magnetic moment for a particular site. Let's say we are considering the pith spin, then magnetic moment of pith value, then the effective magnetic field value, and rate of change of angular momentum, that is called H cross SP, and this is the dispersion relations, and we are going to derive this one. For that, here we consider the pith spin, and so that the exchange energy can be written as that the SP will have a spin sharing with SP minus 1 as well as SP plus 1, so that this will be the term 2j SP dot SP minus 1 plus SP plus 1. So that is the excitation energy at the P side. We can call it as UP. This can be written as UP is equal to minus 2j SP dot SP minus 1 plus SP plus 1. Now we consider the magnetic moment of the site P, so that is mu P, that is minus G mu B SP, and we substitute for SP using this expression here, and you will get this expression, the exchange energy at the P site, and this can be written in this form. Exchange energy is U is equal to minus mu P dot some term here. So actually the exchange energy can be written as U is equal to minus mu P dot BP. So that is the generalized form of the exchange energy. So the corresponding term here is for BP is this one. So that is the effective field or exchange field at the site of the pith spin. If we have the pith spin, there will be a torque acting on the pith spin, so that torque normally we written tau, that is mu cross B, which can also written as H cross ds by dt. It's actually H cross dp by dt in the form of H cross dp by dt, that is the rate of change of where ds by ds is actually H cross the rate of change of angular momentum. Torque is equal to rate of change of angular momentum, so that we can write H cross dsp by dt is equal to mu p cross bp. So this is the magnetic moment at the pith site, and this is the effective field at the pith site. So that this dsp by dt can be written as minus g mu b by H cross sp cross bp, right? And this can be written as 2j by H cross, on substituting here 2j by H cross sp cross, we substitute for bp here, so that sp cross sp minus 1 plus sp cross sp plus 1. So now we need to consider the components, the component for ds by dt along x, y and z directions. For that, we first consider this sp cross sp minus 1. So sp cross sp minus 1 can be in generalized, we can determine in this form. So this is sp cross sp minus 1, right? So we put the component for sp as well as sp minus 1, and the x component of sp cross sp minus 1 will be from this determined, we can this will be spy dot sp minus 1 is z minus spz dot sp minus 1 y. Similarly, the for sp cross sp plus 1, the x component will be this one, and on substituting here we can write the dsp by dt, the x component of dsp by dt will be this one, this term. We simply substituted that. And similarly, we can calculate what is dsp by dt, the y component, as well as the dsp by dt, the z component. So these equations will involve the product of the spins, as you see here. If we consider the amplitude of excitation is very small, that is the x components of sp and the y component of sp is much smaller than s. So actually the spin is the original spin was along the z directions. So we obtain this component will be much smaller, and we substitute SPZ is equal to S, and we can neglect this term, the x component, the product of the x component and y component, because since these individually these terms are smaller, the product will be much smaller, right? So this so that the ds by dt of the z component will involve this product of x and y components, that term should be equal to 0. And here instead of this sp minus 1 z plus sp plus 1 z, we put it 2 times x, 2 times s, that's capital X, and we substituted here, we can form we can write in this form. Similarly, the dsp by dt, the y component will be this one, the z component is neglected. So these are the three equations, and the solution to this equation will be of this form. The x component spx and spy will be in this form, and we can substitute these values here in these two equations. Substitute for derivative d by dt of this spx here, and spx and spy on the right hand side. You will get an equation here where there will be an additional terms in there is a common factor in all these three terms, that is the e raised to I pk minus omega t will be common factor that you can remove, so that you will get these two equations, minus I omega u is equal to this one. And again here we take a common factor 2 outside, and so that this become 4jx by h cross into 1 minus this e raised to ik plus e raised to minus ik by 2 is cos ka, so there will be a cos ka term into v. Similarly, the second term will be minus I omega v is equal to minus 4jx by h cross into 1 minus cos ka into u. So in order to have a non-zero solution for u and v are constants. In this equation, the u and v are constants. The non-zero solution corresponding to determinant of coefficient has to be 0. So that is the determinant for u and v in these two. The first equation is this one, and the second equation is this one. Solving this one, you will get there will be an minus omega square plus 4jx by h cross all square into 1 minus cos ka all square. And when you rearrange this one, you will get h cross omega all square is equal to some 4jx all square into 1 minus cos ka, and h cross omega will be is equal to 4jx into 1 minus cos ka. So this is the dispersion relation for spin waves in one dimensional with nearest neighbor interactions. So we can extend this one for at lower wavelength, that is k is equal to 2 pi by lambda, right, the wave vector. So at lower wavelength ka is much smaller, so that this 1 minus cos ka can be approximated as half ka all square. So on substituting here, you will get h cross omega is approximately 2js a square into k square. So you can see that at lower wavelength, at this value, at higher wavelength and lower k values, this frequency is found to be proportional to k square. So now we can plot this relation, energy versus k relations, the dispersion relations here. The curve will be like this. At lower frequency, it is proportional to k square, and this is the dispersion relation for magnons in a ferromagnet in one dimensional with nearest neighbor interactions. Just like phonon, the quantization of spin waves will result in the energy in this format, that is energy Ek is equal to n plus half into h cross omega, where nk is the number of magnons. So the excitation of magnons corresponds to, so in this case, the excitation of magnons corresponds to reversal of one spin. So that's what we consider here. So this is the dispersion relations for magnons.